Imagine this traveller, you arrive here not by accident, but as if the universe placed this moment gently in your hands. Somewhere beyond the quiet edge of Mars, an object older than our Sun glides through the dark, and behind it, new bodies are multiplying as though the cosmos itself is whispering a warning. What are the odds that 7 comets would arrive together, or that an interstellar wanderer with impossible chemistry would spark a pattern that defies probability? One object moves with a 1 in 20,000 chance trajectory, silent, green and watching. So settle in, observer. The night is wide, and the story is deeper than it seems. Stay with me before you fall asleep. In mid-September 2025, astronomers observed an unexpected pattern emerging within the near-Earth environment. The month was initially forecast to be uneventful, with only routine monitoring of minor bodies and predictable space weather activity. Instead, what unfolded over an 11-day period challenged baseline expectations about the stochastic behaviour of near-Earth objects. The sequence began with asteroid 2020 Phoebus F-Nisu, a substantial object estimated between 130 and 290 metres in diameter. Its passage at 6.8 lunar distances posed no threat to Earth, yet its timing would soon gain significance. Only 4 days later, 2025, RJ2 entered the monitoring zone, passing at an even closer distance of 4.2 lunar distances. The arrivals did not stop there. Additional discoveries, including 2025 QP9, 2025 SD14, and 2 smaller objects detected only after closest approach, revealed a clustering of 6 asteroids in less than 2 weeks. This rate is approximately 3 times higher than the statistical monthly average. Clustering of this scale is rare. Near-Earth objects typically arrive in patterns consistent with random distribution, influenced by long-term gravitational interactions, thermal forces such as the Yarkovsky effect, and slow diffusion processes within the asteroid belt. Yet the September sequence displayed compressed timing and partially overlapping origins when backtracked through orbital simulations. Several objects appear to originate from adjacent regions within the inner main belt, as though perturbed in a similar time frame. Multiple hypotheses were proposed. One possibility involved subtle gravitational resonances propagated through the belt by Jupiter, though this mechanism did not fully explain the tight temporal grouping. Another suggestion involved variations in solar radiation pressure, or elevated geomagnetic conditions related to the G3 storm recorded on September 14-15. Such factors can influence dust and small debris, but their ability to synchronize multi-hundred-meter asteroids remains questionable. Additionally, the Yarkovsky effect, while capable of altering asteroid trajectories over long timescales, generally produces gradual divergences, not sudden coordinated arrivals. The timing of the asteroid wave coincided with escalating anomalies associated with 3I Atlas, the third confirmed interstellar object to enter the solar system. Throughout early and mid-September, Atlas exhibited increasingly unusual behaviour. Its coma expanded to nearly 400,000 kilometres. Its spectral signature intensified in the green region, associated with diatomic carbon emissions. Its chemical composition showed deviations from typical cometary norms, and its thermal activity fluctuated in patterns still under study. While no causal relationship can be empirically established, the coincidence added complexity to the interpretive landscape. The possibility that Atlas's passage through the heliosphere could indirectly influence debris dynamics is intriguing but currently unsubstantiated. Nonetheless, the concurrence of an active interstellar visitor elevated solar activity, and a statistically improbable cluster of near-Earth objects has led some researchers to consider broader systemic interpretations. These include the idea of transient perturbations propagating through the asteroid belt, or emergent interactions between solar cycle forces and interplanetary material. The clustering of September 2025 serves as a reminder that the solar system is not a static environment. Even modest perturbations can generate complex cascades across astronomical scales. While each observed asteroid poses no hazard, the combined pattern underscores gaps in current predictive models and suggests that ongoing monitoring may reveal further deviations as 3I Atlas approaches its Mars flyby and subsequent perihelion. In summary, the September wave represents an anomalous period of increased asteroid activity, whose origins remain uncertain. Whether attributable to natural perturbative mechanisms, coincidental timing, or emergent interactions within the heliosphere, the event encourages continued analysis and highlights the dynamic nature of the solar system during times of heightened interstellar activity. The unusual clustering of asteroids observed in mid-September 2025 prompted a multidisciplinary investigation across planetary science, orbital dynamics, heliophysics, and observational astronomy. Although initial assessments treated the asteroid wave as a statistical anomaly, the persistence of the pattern as well as its timing relative to other rare astronomical events motivated researchers to examine its origins with significantly greater scrutiny. A comprehensive review began with the most conservative assumption that the clustering was coincidental. The first task involved calculating the probabilities associated with 6 near-Earth objects arriving within an 11-day window. Using long-term observational data from the Minor Planet Center, analysts established that the mean monthly detection rate for near-Earth asteroids above 40 meters in diameter rarely exceeds 2 to 3. Even accounting for observational biases and seasonal detection cycles, the probability of 6 such objects passing within measurable proximity to Earth within such a compressed interval was markedly lower than 5%. However, coincidence, while improbable, is not impossible. Therefore, the next step was to examine whether a shared perturbative event might explain the clustering. Researchers modelled scenarios involving solar-induced forces, gravitational resonances, and collisional fragmentation within the asteroid belt. One candidate mechanism involved Jupiter's shifting gravitational influence near perihelion of its orbit. Although Jupiter's mass dominates the structure of the asteroid belt, its perturbations typically manifest over decades, not days. Simulation data from numerical integrators such as Rebound and SwiftN-Body showed no evidence of recent resonance, sweeping, or secular perturbations that could account for the sudden appearance of multiple Earth-crossing trajectories. Another hypothesis focused on solar activity, particularly the G3 geomagnetic storm recorded on September 14, 15. Strong solar wind streams and magnetic field variations can influence small particles, but their effect on multi-hundred-meter bodies is negligible. Nonetheless, an indirect mechanism involving temporary thickening of the interplanetary dust environment was discussed. Increased dust density can marginally affect thermal forces on asteroid surfaces, enhancing the Yarkovsky effect. However, the acceleration scale remains orders of magnitude too weak to synchronize the arrival of several large objects. A third possibility, collisional fragmentation, was evaluated with care. If a parent body within the belt had recently fractured, its fragments could pass near Earth in quick succession. Spectral comparison among the objects in the September wave did not support common ancestry. Albedo measurements, reflectance spectra, and orbital inclinations all showed divergence rather than convergence. The absence of a recent major fragmentation event in the belt further weakened this hypothesis. Having dismissed the more conventional mechanisms, researchers turned their attention to the system-wide context in which the asteroid wave occurred. September 2025 was by any metric an anomalous astronomical month. 2 naked eye novae erupted in the southern sky. A series of powerful earthquakes struck Kamchatka and Venezuela during elevated geomagnetic conditions. And at the centre of ongoing discussion was 3I Atlas, an interstellar object exhibiting chemical and photometric behaviour that remains the subject of active debate. While there is no accepted model supporting causal connections between interstellar objects and asteroid belt dynamics, the coincidence in timing raise legitimate questions. Interstellar objects carry unique charge distributions, volatile compositions, and large-scale coma interactions not typically seen among objects native to the solar system. As 3I Atlas moved deeper into the heliosphere, its coma expanded to several 100,000 kilometers, interacting with solar wind streams and potentially altering local plasma densities. Could this interaction propagate through the heliosphere in a way that indirectly perturbed near-Earth objects? No empirical model currently supports such a pathway. Yet the plasma environment of the heliosphere is neither uniform nor static. Large comae can influence solar wind flow, generating turbulence, and transient magnetic irregularities. The possibility that these disruptions could propagate into the asteroid belt even weakly has not been conclusively evaluated. At minimum, the simultaneous appearance of multiple anomalies called for careful attention rather than premature dismissal. Adding further complexity was the fact that several September objects, when traced backward, appeared to originate from regions of the belt that had experienced mild gravitational stirring in early August. Although not widely publicised at the time, a series of minor perturbations in semi-major axes were detected among multiple belt objects variations small enough to avoid media attention, yet large enough to be of interest to specialists. Some researchers interpreted these perturbations as the tail end of a resonant interaction that had been building for months. Others argued for a solar driver, pointing to the increasing activity approaching the peak of solar cycle 25. Still others admitted reluctantly that unexplained variances are not uncommon in long-term asteroid monitoring, but typically not in such a concentrated temporal window. Parallel to these debates, observational programs expanded. The Pan-STARRS survey increased nightly sky coverage by 18%. The Atlas network added new follow-up cadence for potentially hazardous objects. Amateur astronomers across the globe contributed valuable astrometry, helping refine orbital elements with remarkable precision. The September wave catalysed a rare global collaboration blurring lines between professional and amateur science in pursuit of clarity. As the investigation progressed, one central insight crystallised. The September wave was not simply a concern about 6 asteroids. It was evidence of a system responding to forces that may not yet be fully understood. It served as a reminder that the solar system is dynamic, not static. Its structures, though predictable at large scales, are sensitive to perturbations both internal and external. When multiple anomalies cluster in time, researchers must reconsider assumptions, refine models, and remain open to interpretations beyond the standard canon. With 3 Atlas approaching its Mars flyby on October 3rd, the scientific community faces an unprecedented opportunity to observe correlations, or lack of correlations between interstellar dynamics and solar system behaviour. Whether the September asteroid wave represents coincidence, emergent complexity, or the early signature of a larger pattern remains uncertain. What is clear is that continuous monitoring, empirical scrutiny, and cautious open-mindedness will be essential in the months ahead. While the September asteroid wave commanded immediate attention due to its proximity and potential implications for planetary defence, a parallel development was unfolding in the background, an unusually active period for cometary bodies. Throughout early and mid-September, several long-period comets showed unexpected brightening fragmentation or trajectory deviations, each subtle on its own, but collectively forming a pattern that merited careful examination. The most prominent among them was Comet C 2025 R2 SWAN, a volatile-rich object first identified by the Solar Wind Anisotropies instrument aboard SOHO. SWAN is not a dedicated comet hunting instrument. Its primary function is to map hydrogen emissions from solar wind interactions. Comets only enter its field of perception when they release enough hydrogen-rich vapour to register as distributed glow across heliospheric maps. For SWAN to detect a comet, significant sublimation must already be underway. Thus, the detection of C 2025 R2 on September 11th suggested that the comet had activated earlier or more violently than expected for its orbital stage. When astronomers attempted to model its sublimation curve, they found that the rate of volatiles released was inconsistent with simple solar heating. Some argued that the comet's surface may have experienced a rapid transition, perhaps the collapsing of a crust layer, or the sudden exposure of volatiles previously insulated from solar radiation. What made the case particularly interesting was that 3 other comets, all unrelated by orbital lineage, reported similar irregularities between late August and mid-September. 2 brightened more rapidly than predicted. One showed signs of rotational instability, though each anomaly could be attributed to local conditions on a case-by-case basis. The temporal clustering raised familiar questions. Were these simply isolated quirks coinciding by chance, or signals of a broader environmental change within the inner heliosphere? To answer this, researchers examined solar wind variability during the period. Solar cycle 25 had entered a phase of increasing complexity. producing stronger than normal coronal mass ejections and elevated proton flux. These disturbances can affect cometary surfaces by transferring energy to loosely bound dust layers, changing sublimation dynamics, or in extreme cases triggering fragmentation events. Preliminary correlations between solar wind spikes and comet activation patterns offered partial explanations, but the match was imperfect. Several activation events occurred during magnetically quiet intervals, times when solar forcing should have been minimal. As astronomers pieced together these observations, a more subtle realization emerged. See Donnerstag 2025. R2 was only part of a larger picture. The September sky was unusually populated not only by comets, but also by a dense background of faint newly catalogued objects, some likely dormant comets, others small asteroids with high volatile content. The Vera C. Rubin Observatory, still in commissioning at the time, had begun to reveal the true density of low-albedo objects in the inner solar system. Many had been overlooked by previous surveys due to their faintness, their chaotic orbits, or their rapid transient appearances. This influx of detections did not necessarily imply an actual increase in population, yet it contributed to the sense that the solar system was suddenly more active, more crowded, more dynamic. Solar system science had always acknowledged that comets arrived in stochastic waves due to perturbations in the distant Oort cloud, but such waves typically unfold on timescales of centuries, not weeks. Against this backdrop, another figure loomed over the scientific landscape: asteroid 99942, Apophis, the 400-meter near-Earth object scheduled for a remarkably close Earth flyby in 2029. Although Apophis posed no imminent impact threat, the object remained a touchstone for public and institutional awareness of planetary defense. Its impending encounter underscored how gravitational resonances, secular drifts, and minor orbital deviations could accumulate into profound dynamical consequences. Apophis served as a reminder that even predictable celestial bodies require ongoing monitoring, and that unusual patterns such as the September surges should not be dismissed lightly. The convergence of heightened comet activity increased near-Earth detections, and an interstellar object moving toward perihelion prompted researchers to consider whether multiple drivers might be overlapping, each contributing to the broader sense of anomaly. However, speculation, particularly regarding causal links, demanded discipline. Notably, early discussions attempting to connect the comet surge to 3I Atlas were met with skepticism. Unlike comets bound to the solar system, interstellar objects do not share long-term orbital histories or resonant relationships with solar system bodies. Atlas's influence, gravitational or otherwise, is negligible, at heliocentric distances exceeding hundreds of millions of kilometers. Its presence alone could not explain the rise in cometary activation events. Still, the field did not entirely dismiss the possibility of indirect environmental effects. One line of inquiry examined whether Atlas, with its large and chemically unusual coma, might interact with solar wind structures in ways that produce downstream turbulence. While unlikely to affect comets near Earth, such disturbances could potentially propagate through the heliosphere, influencing dust densities or magnetic structures in subtle ways. This idea remained theoretical. No model yet demonstrated such a pathway with quantitative rigor. Yet, it was noted and filed for future modelling. The broader scientific value of this period lay not in any single anomaly, but in how these anomalies interacted to challenge assumptions. For decades, researchers viewed the inner solar system as relatively stable. Its small body population largely catalogued its dynamics well understood. The September surge, combined with C-125 Tamku's irregular behavior and 3I Atlas's unique chemistry, reminded scientists that the solar system is part of a larger dynamic galactic environment, continuously shaped by forces operating on scales far beyond human intuition. Cometary activity, especially among first-time visitors from the outer solar system, has always served as a window into primordial chemistry and volatile distribution. Now, with the prospect of more frequent interstellar visitors, the boundary between solar system science and galactic archaeology is beginning to blur. Each new activation event, whether caused by solar forcing or internal structural change, carries implications for how volatiles behave under extreme long-term cosmic conditions. By late September, the observational focus began to shift from the asteroid wave to the upcoming period of maximal activity, the dual perihelia of Swan and 3I Atlas, as well as a suite of smaller comets approaching their closest solar distances. These events promised fresh data at the cost of increased observational difficulty due to solar glare. For researchers, the task ahead was clear, but demanding continued monitoring the comet's surge-refine models of volatile activation and prepare for the challenge of observing multiple objects during their brightest but least accessible phase. The next several weeks would determine whether the September anomalies were precursors to a broader environmental trend or merely a transient clustering underscored by exceptionally sensitive instrumentation. Either interpretation would yield valuable insights. The scientific method does not require the universe to behave unusually. It requires only that scientists remain attentive when it does. As astronomers worked through the unusually dense activity of September 2025, one object rose decisively above the rest, not because it posed danger, nor because it behaved erratically, but because it did not belong to our solar system at all. This was 3R Atlas, formerly designated C2025 N1, only the third confirmed interstellar object in human history. Its discovery on July 1st by the Atlas survey in Chile appeared ordinary at first. The automated pipeline flagged it as routine near-Earth or long-period comet candidate 1 among many faint detections produced each night. Only when follow-up observations refined its orbit did a critical parameter reveal itself. Its eccentricity exceeded 1.0. In celestial mechanics, this marks an object travelling too fast to ever be captured by the Sun. A hyperbolic trajectory is the unmistakable signature of something unbound and object passing through the solar system rather than belonging to it. The confirmation of interstellar origin triggered an immediate shift in observational priorities across major observatories. What made the object particularly promising was its approach geometry. Atlas would reach perihelion in late October and then re-emerge from solar glare in December, when Earth and Sun would be positioned favourably for extended observation. Interstellar objects are usually fleeting. Their brightness windows are short and opportunities for detailed study vanish quickly. Atlas, by contrast, offered months of visibility at scientifically productive distances. Even before its chemistry was known, size estimates from the Hubble Space Telescope suggested that Atlas could be significantly larger than its predecessors 1Y, Oumuamua and 2I Borisov. Although the 5.6-kilometre upper bound was likely an exaggeration caused by coma effects, the nucleus was still believed to be several kilometres across. A large nucleus contains more volatiles and preserves deeper layers, potentially holding material formed under conditions far different from those around the Sun. Once spectroscopic data arrived in late summer, Atlas's scientific value expanded dramatically. Observations from the James Webb Space Telescope revealed a coma dominated by carbon dioxide with CO2 to H2O ratios among the highest ever recorded in any comet. In the inner solar system, water normally dominates cometary activity. Carbon dioxide plays a secondary role. The inversion of this pattern indicated extreme formation conditions, either in a distant outer disk region or a protoplanetary environment, colder and chemically different from our own. Such chemistry could not be fully explained using solar system templates. Complementary results from the Very Large Telescope added further complexity. The emission spectra showed unexpectedly strong nickel lines with weak iron signatures. In solar system comets, the two metals typically occur in roughly solar proportions. The mismatch suggested either formation around a star with non-solar metallicity or significant chemical alteration during an extended interstellar journey. These characteristics supported early modelling that placed Atlas's likely origin in the Milky Way's thick disk. A population of older, lower metallicity stars formed long before the Sun. As autumn progressed, observatories documented evolving coma structures, dust jets emerging at unusual angles, tail bifurcations, and irregular brightness fluctuations. These features hinted at a nucleus composed of multiple volatile layers or chemically distinct regions. While none of these behaviours were unprecedented individually, the combination interstellar origin extreme chemistry and complex outgassing made Atlas an object with few meaningful analogues. The timing of its arrival, coinciding with the September asteroid surge, prompted speculation beyond scientific circles, yet gravitational calculations quickly ruled out causal links. Atlas's mass and distance were insufficient to perturb near-Earth objects in any measurable way. Its influence was several orders of magnitude weaker than the background gravitational noise produced by the planets. Scientists therefore cautioned against attaching meaning to the coincidence. Observational clustering often appears dramatic precisely because detection capabilities have improved. Still, researchers considered whether the coincidence might reflect broader heliophysical changes. Solar Cycle 25 showed elevated activity including enhanced solar wind and episodic particle flux. Such conditions can influence comet behaviour, but would not connect Atlas to near-Earth asteroids directly. In the absence of compelling evidence, the scientific perspective remained conservative. The timing was interesting, but correlation did not imply causation. Understanding Atlas's significance required situating it within the history of interstellar object research. Before 2017, these visitors were predicted in theory but invisible in practice. Oumuamua and Borisov provided the first direct detections but offered limited observation time. Atlas, by contrast, approached in a manner that allowed unprecedented multi-wavelength characterization, effectively functioning as a rare natural sample return from another star system. Its extended observation window enabled detailed study of sublimation curve, show volatile output changes with solar distance. These trends matter because materials formed in different stellar environments respond differently to solar heating. Atlas seemed likely to reveal volatiles that only activate at very low temperatures, providing data that could inform models of protoplanetary disk chemistry beyond the Sun's influence. Rotational studies added another layer of interest. The object's light curve implied either slow rotation or a non-principal axis tumbling state. Both possibilities were scientifically valuable. A tumbling rotation often reflects past collisions or long-term torque accumulation during interstellar travel. Rotation influences sublimation patterns, dust release and internal structural stresses, key components in understanding comet longevity. By early October, consensus had formed around Atlas as a uniquely valuable interstellar probe. Researchers from astrochemistry, galactic evolution, planetary science and dynamical astronomy converged on the same conclusion. The object offered direct empirical access to material shaped by conditions outside the solar system, possibly older than Earth itself. Its approach raised fundamental questions. How diverse are planetary formation environments across the galaxy? How do volatile inventories differ among stars of different metallicity? What happens to ices and refractories after billions of years in interstellar space? And perhaps most importantly, how representative is Atlas of the larger interstellar population? By late October, solar glare made further observation impossible, forcing astronomers to wait for the December re-emergence. That phase would determine whether the object had survived perihelion intact, and whether its chemistry changed under peak heating data that could reshape our understanding of planetary formation at galactic scales. The weeks surrounding perihelion were expected to be the most revealing phase of 3i Atlas's journey, yet paradoxically the most observationally inaccessible. As the interstellar object moved deeper into the solar glare in late October, telescopes were forced to suspend direct monitoring. This period allowed scientists to shift focus from raw data collection to theoretical interpretation, building preliminary models to explain the object's unusual chemistry and its early outburst behaviour. Several lines of inquiry emerged, converging on three central questions. What internal structure produced the observed volatile ratios? What role did interstellar processing play? And how did the nucleus respond to solar heating after billions of years in deep freeze? The extreme carbon dioxide dominance was the first puzzle. In most solar system comets, water ice becomes the primary driver of activity as they approach 2-3 AU from the Sun. Atlas, however, displayed strong CO2 lines even beyond this range and comparatively weak H2O signatures. Researchers proposed two broad categories of explanation. The first involved primordial formation conditions. Atlas may have formed in a region of its parent disk where temperatures never rose high enough for significant water ice accumulation. This would place its birthplace far beyond the CO2 snowline, perhaps in a cold outer ring, analogous to the extreme outskirts of the solar nebula. If so, Atlas's composition could reflect a class of volatile rich planetesimals rarely seen in our own system. The second possibility involved post-formation alteration during interstellar transit. Cosmic ray bombardment continuous over billions of years can gradually modify surface layers through radiolysis. Water molecules are more susceptible to such processing than CO2, and long-term exposure could selectively deplete H2O while preserving carbon dioxide and carbon-bearing compounds. This mechanism aligns with observed trends in laboratory analog experiments, though scaling these results to billion-year timescales remains uncertain. What strengthened this hypothesis was the detection of unusual isotopic ratios in preliminary JWST data ratios, consistent with extended exposure to high-energy particles. Another key anomaly involved the object's metallic composition. The strong nickel emissions paired with weak iron signatures challenged assumptions about elemental distribution in cometary materials. In the solar system, nickel and iron appear in nearly identical proportions because they condense under similar conditions in protoplanetary disks. The imbalance detected in Atlas could reflect non-solar metallicity in its parent stellar population, consistent with thick disk chemistry. Stars in the thick disk possess lower metallicity overall, but vary widely in their nickel to iron ratios, sometimes significantly deviating from the Sun's composition. If Atlas formed around such a star, its metal content could represent direct evidence of a chemically distinct environment. Alternatively, selective iron depletion could occur through interstellar sputtering. Iron atoms, particularly in silicate grains, are more easily liberated by dust impacts than nickel, which may survive longer in certain molecular complexes. Over geological timescales, countless micro-collisions with interstellar dust could reshape the surface elemental profile, especially in the uppermost layers that dominate spectroscopic measurements. These hypotheses required testing, and the perihelion interval provided an ideal moment for dynamic modelling. With direct observation paused due to solar interference, researchers constructed thermal evolution simulations to predict how Atlas might respond to intense solar input. The central question was whether the nucleus would remain intact. Comets entering the inner solar system for the first time often experience structural failure due to rapid heating, internal pressure imbalances, or rotational stresses. Atlas, however, had unique properties, potentially significant size, long-term exposure to cosmic rays that might have compacted surface layers and volatile content that could drive sublimation unevenly across the nucleus. Model outputs varied widely depending on assumptions about internal porosity. Highly porous nuclei tend to shed material, gradually absorbing stress through distributed collapse, whereas denser bodies are more likely to experience sudden fracturing. Atlas could plausibly fall anywhere along this spectrum. Several models predicted partial fragmentation, splitting into two or more large pieces that would later diverge in brightness curves after perihelion. Others suggested full survival, but with substantial reconfiguration of the surface as CO2 reservoirs migrated or vented rapidly. The most conservative scenario expected minor morphological changes, but no catastrophic breakup. Parallel to this modelling effort, researchers analysed coma asymmetries documented before perihelion. Some jets appeared to originate from rotationally inconsistent regions, suggesting internal heterogeneity or complex topography. If the object were tumbling episodic in sunlight exposure could trigger volatile release at irregular intervals. This matched earlier brightness oscillations seen in light curve analysis. However, the precise rotation state remained unresolved. The pre-perihelion data window was too narrow to capture a full cycle, especially if the period exceeded several days or if the nucleus exhibited non-principal axis rotation. In addition to nucleus modelling, the perihelion hiatus prompted broader discussions about the implications of interstellar comet activity for galactic chemistry. Atlas's composition, regardless of the details, confirmed that planetary systems outside the solar system produce a variety of icy bodies with chemical signatures unlike anything found locally. This realization strengthened the emerging perspective that interstellar objects might serve as direct samples of exoplanetary processes, materials shaped not by theory or indirect inference, but by actual conditions beyond the Sun's influence. The timing of Atlas's visit, coinciding with improvements in survey technology, encouraged speculation about future detection rates. Some researchers propose that objects like Atlas may pass through the solar system more frequently than previously believed, simply escaping notice due to limited observational sensitivity. The Rubin Observatory's early detection spikes supported this possibility. If interstellar debris is indeed abundant, the galaxy might operate a natural mechanism for distributing planetary materials across stellar systems. Such a mechanism could influence the dispersion of volatiles, organic molecules, or even prebiotic chemistry. As October came to a close, the scientific anticipation surrounding Atlas grew. Although direct observation was impossible, the object's trajectory was well constrained. It would pass within 0.24 AU of the Sun before fading behind the bright solar envelope. The real uncertainty lay in its reappearance. Would Atlas remain intact, offering the December observing window that researchers had spent months preparing for, or would it fragment into unrecognizable debris, depriving astronomers of the chance to analyze pristine interstellar material? The answer would have implications far beyond cometary science. If Atlas survived, it would serve as a detailed case study in interstellar material resilience, informing models of galactic mixing and long-range volatile transport. If it fragmented, the debris patterns could illuminate internal structure, compositional stratification, and mechanical properties shaped by billions of years in deep interstellar space. In either outcome, the scientific community remained aligned on one point: the existence of objects like Atlas challenges long-standing assumptions about the isolation of planetary systems. The solar system is not a closed laboratory, but a permeable participant in a galaxy-wide network of material exchange. For the first time in human history, the tools existed to study these connections directly. The next phase, Atlas's December re-emergence, would determine whether the questions raised during this brief, intense period of analysis would find answers or whether new mysteries would arise in their place. The temporary loss of direct visibility during perihelion placed unusual emphasis on the upcoming December re-emergence, and anticipation only grew as researchers analysed every possible outcome of the object's solar encounter. Yet while the scientific community waited for Atlas to return to the night sky, attention turned simultaneously toward a broader framework of the state of planetary defence in late 2025. The September surge had highlighted strengths and weaknesses in detection networks, and Atlas's arrival provided a unique opportunity to evaluate how interstellar visitors fit into existing models of solar system risk assessment. The most striking vulnerability exposed during the autumn activity was the solar blind spot, the region near the Sun, where ground-based telescopes struggled to detect incoming objects. This blind spot had been responsible for the surprise arrival of the Chelyabinsk impactor in 2013. And although detection systems had greatly improved since then, the fundamental constraint remained. Optical observatories cannot effectively search the sky within roughly 45 degrees of the Sun due to atmospheric scattering and overwhelming solar brightness. Any object approaching from this direction remains largely invisible until it is too close for meaningful intervention. FA-22 fortunately did not use this corridor. Its trajectory brought it in from a favourable angle, allowing weeks of tracking time, but several of the smaller September objects approached along paths partially aligned with the solar glare, enough to reduce warning periods from weeks to days. These instances reignited debates about the global readiness of planetary defence systems. Despite increasing catalogue completeness for kilometre-scale objects, the majority of 100-300 metre city-killer asteroids remained undiscovered. Objects of this size are capable of causing regional devastation and are statistically far more common than larger bodies. This recognition prompted renewed focus on space-based infrared detection, the only practical solution for closing the sunward blind spot. NASA's NEO Surveyor, mission scheduled for launch in 2027, would operate from a vantage point trailing Earth in its orbit, able to detect warm asteroid surfaces against the cold backdrop of space. Unlike optical telescopes, infrared instruments can identify objects regardless of visible lighting conditions, making them ideal for spotting threats hidden in the solar direction. The September events underscored the urgency of deploying such systems as early as possible. Meanwhile, the Vera C, Rubin Observatory continued to expand the boundaries of what ground-based surveys could achieve. Even in partial operation, Rubin's wide-field imaging produced more small-body detections in hours than some older surveys achieved in months. These discoveries revealed not only the abundance of low-albedo asteroids, but also their tendency to cluster in short detection windows, creating the impression of sudden cosmic busyness. Scientists recognized that this clustering was likely a reflection of improved sensitivity rather than actual increases in near-Earth activity. Yet the effect on public perception, compounded by media narratives linking Atlas to the asteroid surge, made clear the need for careful communication. Indeed, communication itself emerges one of the most important and least predictable components of planetary defense readiness. During FA-22's approach, multiple agencies issued preliminary risk assessments. Although the object was rapidly downgraded to a non-hazardous trajectory, early reporting triggered disproportionate media responses. Some outlets ignored the initial warnings entirely, others exaggerated the threat. Balancing transparency with calmness proved challenging. Scientists emphasized that public communication must convey both uncertainty and context. An object under early investigation may have a non-zero impact probability, yet revisions are expected as more data becomes available. The September surge functioned as a practice scenario exposing both strengths and weaknesses in global coordination. Observatories across multiple continents shared data effectively narrowing orbital uncertainties within days. The International Asteroid Warning Network, IEWN, though still developing, demonstrated its ability to disseminate information rapidly, but media fragmentation, inconsistent messaging, and competing national narratives revealed gaps that could be dangerous during a genuine emergency. The surge also reawakened a long-standing question in planetary defense: how many simultaneous threats can the system handle? The September window saw dozens of objects tracked at once, many with low but non-zero impact probabilities. While computing systems handled the load, analysts noted that decision-making frameworks would be strained in scenarios involving multiple high-priority objects. Deflection missions, particularly kinetic impactors like the DART spacecraft, require years of lead time, precise knowledge of target properties, and coordinated international effort. If a cluster of medium-sized objects were detected approaching within a short interval, current capabilities might prove insufficient. These concerns were amplified by the recognition that long-period comets posed a separate, underappreciated risk category. Unlike near-Earth asteroids, which have well-understood orbital families, long-period comets can arrive with little warning high speeds and large sizes. Many travel on trajectories that bring them close to the Sun before turning toward the inner solar system. Because they spend most of their lives in remote dark regions, they often become visible only months before perihelion. The September brightening of C2025D, though, not inherently threatening, served as a reminder that comet behavior is volatile, complex, and difficult to forecast. Returning to interstellar objects, Atlas did not fit into standard hazard models. Its hyperbolic trajectory ensured it posed no impact threat, and its chemical and physical properties fell outside the scope of traditional planetary defense strategies. Yet its very presence forced scientists to re-examine underlying assumptions. Interstellar objects are unpredictable in frequency composition and thermal behavior. As survey sensitivity improves, the number of detected interstellar visitors will likely increase, raising questions about how often such objects pass through undetected, whether they contribute to local impact risk, and how their chemical diversity might challenge existing classification systems. Atlas became a case study in how planetary defense and interstellar science intersect. On one hand, its non-gravitational outgassing effects, though modest compared to Oort cloud, comets provided valuable insight into modelling forces that complicate orbital predictions. On the other, its alien chemistry highlighted how deflection strategies designed around solar system materials might require re-evaluation if future interstellar visitors were to arrive on more concerning trajectories. Most researchers viewed this as a theoretical scenario, but planetary defense increasingly requires preparation for low probability, high impact possibilities. Throughout the autumn, these discussions converged into a broader understanding. The solar system operates within a dynamic galactic environment, and planetary defense cannot be isolated from that reality. Interstellar objects like Atlas serve as reminders that the solar system is permeable, exposed to material exchanged across stellar neighbourhoods over billions of years. Even if Atlas posed no direct danger, its arrival during a period of heightened small-body activity encouraged researchers to explore how local and galactic processes overlap. As November approached and the Sun swallowed the last visible traces of Atlas, the scientific community entered a period of calculated anticipation. The object was on track to re-emerge in the pre-dawn sky by early December, and with it the opportunity to test months of theoretical predictions. Would the nucleus remain intact? Would volatile ratios shift under solar heating? Would the tail structure reveal new clues about internal stratification or asymmetric jets? These questions would not only shape the final interpretation of Atlas itself, they would influence models of comet physics, interstellar chemistry, and planetary defense readiness for years to come. As November progressed and 3 Atlas disappeared fully into the solar envelope, researchers shifted their attention toward the unusual behaviors the object displayed during its inbound trajectory. Even before perihelion Atlas had begun to challenge long-standing assumptions about comet physics, its early brightening episodes, complex tail geometries, and volatile-driven jets did not simply expand existing models. They exposed the limitations of those models when applied to materials originating beyond the solar system. The next phase of analysis involved cataloguing and interpreting the anomalies with care, recognizing that what appeared anomalous relative to solar system norms might be entirely ordinary for objects formed under different astrophysical conditions. The first category of unusual behavior involved volatile activation. Traditional comet models predict a fairly smooth increase in brightness as a comet approaches the Sun, with water sublimation dominating the activity inside approximately 3 AU. Atlas, however, displayed episodic brightening events that did not align with simple, heliocentric distance curves. These flare-ups suggested internal processes occurring beneath the surface, such as sudden exposure of volatile pockets or collapse of insulating crust layers. Because CO2 sublimates at significantly lower temperatures than water ice, even small cracks or shifts in the nucleus could produce abrupt increases in gas and dust output. Such behavior is not entirely unknown among solar system comets, but the frequency and amplitude of Atlas's events were higher than expected. Dust-jet asymmetry provided additional clues. High-resolution imaging in September revealed multiple jets emerging from spatially distinct regions of the nucleus, some oriented in directions inconsistent with the object's estimated rotation axis. These jets produced observable deviations in tail morphology, at times creating bifurcated structures with differing particle size distributions. Polarimetric analysis suggested a mixture of fine dust grains and larger aggregates being released simultaneously, a pattern indicative of heterogeneous layering within the nucleus. This layering, if confirmed, could support either a primordial origin in a chemically diverse protoplanetary disk, or a long history of processing through interstellar radiation and microcollisions. Another remarkable characteristic involved the object's rotation state, which remained elusive throughout the observational window. Photometric light curves returned inconsistent periodicities, pointing either to an unusually long rotation period or a non-principal axis tumbling condition. Tumbling behavior can result from past impacts or a symmetric volatile release over extended timescales. For an interstellar object, either explanation was plausible. If Atlas had spent billions of years drifting through interstellar space, occasional dust grain collisions could have gradually altered its angular momentum. Conversely, if its formation environment involved multiple close encounters with larger bodies, early collisions could have imparted complex rotational motion that persisted due to negligible damping forces in the interstellar medium. The inability to determine a definitive rotation period reflected not only observational challenges, but also the possibility that Atlas did not conform neatly to rotational categories developed for solar system bodies. Chemical analysis continued to challenge expectations. JWST's detection of extreme CO2 dominance raised the question of whether Atlas might contain volatiles uncommon in solar system comets such as COCH4N2 or other ices that sublimate at exceptionally low temperatures. If such volatiles existed within the nucleus, they would likely become detectable only after perihelion, when deeper layers experience sufficient heating. Researchers prepared for the possibility that the December re-emergence might reveal a second phase of activity distinct from the early CO2-driven phase, providing insight into stratified ice composition. Such a transition could offer unprecedented data about the physical and thermal structure of interstellar planetesimals. The nickel-ion imbalance remained a central puzzle. While selective surface depletion remained a plausible explanation, some researchers explored alternative pathways. One hypothesis involved fractional condensation in the parent system's protoplanetary disk. In colder disks or disks with unusual elemental gradients, certain metals may condense preferentially into stable molecular or crystalline forms, leading to non-solar abundances in smaller bodies. If Atlas originated in such an environment, its metal composition could reflect conditions not typically found around Sun-like stars. This possibility aligned with kinematic modelling that suggested a thick disk origin, where stars exhibit a broader range of elemental ratios due to early galactic evolution and incomplete mixing of supernova ejecta. In parallel with chemical considerations, researchers examined the broader category of comet outbursts. Outbursts in solar system comets often signify structural tension phase transitions or collapse of subsurface voids. Atlas's outbursts, however, were notable for their timing. Some occurred at distances where water sublimation should be minimal, implying that CO2 or other volatiles dominated internal pressure buildup. If deeper reservoirs were capped by rigid crust layers formed during interstellar processing, heating could eventually induce pressure spikes that fracture the surface, releasing gas and dust in sudden bursts. These events could influence rotation-alter coma morphology and impact trajectory predictions through non-gravitational acceleration. Non-gravitational forces represent a critical consideration in modelling any comet's path. And for interstellar objects, the issue becomes even more significant. Even smaller symmetries in gas outflow can produce measurable trajectory deviations, complicating orbit forecasting. Atlas showed some evidence of such forces, but the degree of deviation remained modest compared to Oumuamua, whose unexplained acceleration had sparked extended debate. For Atlas, the presence of visible sublimation and well-characterized volatile output allowed these forces to be modelled within conventional frameworks. The researchers acknowledged that post-perihelion data would be required to refine these calculations. Atlas's behaviour also encouraged deeper exploration of how interstellar travel modifies the mechanical properties of comet nuclei. Interstellar radiation exposure can darken surfaces, reduce volatile abundance at shallow depths, and compact microstructures, increasing tensile strength. A denser crust could delay sublimation until sufficient heat penetrates deeper layers, making activity more abrupt when it does occur. Such behaviour could explain Atlas's sudden activation episodes. It might also influence whether the object survived perihelion. A strong crust could protect the nucleus from rapid disintegration, while an internally fractured structure could undermine stability when heated intensely. Across all these analyses, a central theme emerged. Atlas did not simply behave like a strange comet, it behaved like a comet, whose history spanned physical regimes absent in the solar system. The combination of exotic chemistry, atypical volatile activation, irregular rotations, and interstellar processing effects formed a coherent picture of an object shaped by conditions vastly different from those that govern solar system comets. By late November, the scientific narrative had crystallized. Atlas was not an anomalous outlier. It was a data point in an emerging new category, interstellar planetesimals, whose properties reflect the diversity of planetary formation environments across the Milky Way. The December re-emergence would not merely confirm the object's structural survival, it would determine whether astronomers could examine deeper layers, refine chemical models, and identify whether Atlas represented a rare exception or a common archetype of interstellar debris. All that remained was to wait as the object passed behind the soon its behaviour, hidden its structure unknown, its future contribution to science suspended in the radiance of the star it had travelled so far to encounter. As researchers finalised their pre-perihelion analyses of through-Atlas discussions, inevitably turned toward a more speculative question, one that tends to surface whenever an astronomical object displays unfamiliar properties. Could any aspect of Atlas's behaviour be interpreted as evidence of artificial origin? The question itself was not taken seriously by most scientists, but its persistence in public discourse required a clear, rigorous evaluation. Understanding why certain behaviours seem mysterious and why those impressions rarely translate into legitimate scientific anomalies became an important part of contextualizing Atlas within the broader landscape of interstellar research. Historically, any celestial phenomenon that defied immediate explanation has been subject to conjecture about intelligent design or extraterrestrial technology. Oumuamua's unexplained non-gravitational acceleration in 2017 triggered several years of debate, in part because its trajectory and shape presented observational challenges that could not be resolved with available data. Atlas, however, presented no such ambiguities. From the beginning, its behaviour aligned with known physical processes, albeit at the extreme end of the distribution. Every volatile emission, every photometric fluctuation, and every coma feature corresponded to established models of comet behaviour, even if those models required adjustment for non-solar chemistry. Nevertheless, it was important to address the speculative interpretations methodically, both to correct misconceptions and to clarify the boundary between legitimate scientific uncertainty and unfounded inference. One of the earliest claims circulating on social media involved the idea that Atlas's perfect timing for observation implied purposeful delivery. The argument followed that an object arriving precisely when humanity possessed advanced telescopes must be more than coincidence. Statistically, however, temporal clustering is expected once detection capabilities improve. If interstellar objects pass through the solar system regularly, most would have gone unnoticed before 2017. Improved surveys such as Atlas Pan-STARRS and soon Rubin dramatically increased the probability of detecting such objects. The perception of a sudden influx is therefore a detection artifact, not a physical trend. Another line of speculation centered on Atlas's unusual chemical composition, particularly its high carbon dioxide content and low iron abundance. Yet chemical variance across planetary systems is well documented in exoplanet research. Host stars exhibit a wide range of metallicity ratios, which directly influence the distribution of the elements available during planet formation. Moreover, protoplanetary disks possess radial temperature gradients that produce distinct condensation fronts. A body forming far beyond the water ice line would naturally accumulate CO2-rich ices. None of this requires artificial modification. If anything, Atlas's volatiles reinforced theoretical predictions about chemical diversity across the Milky Way. Claims of artificiality also leaned heavily on the object's non-principal axis rotation. Tumbling, however, is not only common among small bodies, but often expected for interstellar objects. Collisional histories in dense star-forming regions, combined with billions of years of torques from sublimation asymmetries, make stable rotation states improbable over long timescales. Furthermore, tumbling is detrimental to controlled navigation. No spacecraft intentionally maintains a non-principal axis rotation, as it complicates power generation and attitude control. Atlas's rotational irregularities, far from suggesting technology, served as evidence of natural dynamical evolution. Trajectory analysis provided an even clearer dismissal of artificial origin hypotheses. Atlas followed a clean, hyperbolic orbit, consistent with gravitational interaction alone. There were no measurable course corrections, no deceleration or acceleration inconsistent with sublimation-driven forces, and no inflections that might indicate controlled motion. Every deviation in trajectory fell within predictive margins once outgassing effects were incorporated. If Atlas had been maneuvering intentionally, those adjustments would have produced detectable anomalies in Doppler tracking or positional residuals. None were observed. The absence of electromagnetic emissions further weakened artificiality claims. Radio observatories performing routine scans detected nothing beyond thermal noise and expected molecular lines. No structured signals, no narrowband frequencies, no modulation patterns, and no coherence indicators were present. The electromagnetic environment around Atlas matched what one would expect from a natural comet with active sublimation. In comparison, even malfunctioning spacecraft produced detectable communication artifacts. Atlas emitted none. Why then did these ideas gain traction in public discussions? The answer lay partly in the object's narrative context. Atlas arrived during a period of heightened awareness of near-Earth objects, shortly after a cluster of asteroid detections, and during a time of increased solar activity. The combination created an illusion of interconnectedness. Humans are predisposed to detect patterns, especially when confronted with events that seem statistically improbable. The coincidence of an interstellar visitor appearing amid an asteroid surge reinforced a sense that the universe was signaling something. In reality, unrelated processes, improved survey coverage, natural clustering of asteroid approach geometries, and a well-timed interstellar trajectory simply overlapped. The psychological component became more evident when examining the language surrounding the object. Words like unprecedented, anomalous, and mysterious, though scientifically accurate in describing Atlas's novelty, often carry connotations of intentionality. Scientific unfamiliarity is easily mistaken for impossibility, yet the field of astrochemistry demonstrates that unusual does not imply unnatural. It merely reflects limited sampling. Before 2017, humanity had no confirmed interstellar objects in its catalogues. After 3 detections in less than a decade, it became clear that the solar system interacts with the galactic environment more frequently than previously assumed. The artificial origin hypothesis also overlooked an important physical constraint. Interstellar travel by macroscopic spacecraft is extraordinarily expensive in terms of energy. The velocities required to cross stellar distances produce hazardous conditions for any constructed object. Dust impacts at tens of kilometers per second possess kinetic energies capable of vaporizing metal surfaces. A fragile, volatile, rich body like Atlas could not survive interstellar transit if it were intentionally engineered. Its structure matched what would be expected of a natural planet, tesimal, porous, icy, and prone to outgassing, precisely the opposite of engineered durability. At a deeper scientific level, addressing these speculative interpretations served a practical purpose. The scientific process must distinguish curiosity-driven questions from those that misconstrue physical constraints. Investigating Atlas's properties rigorously allowed researchers to refine models of interstellar material without introducing unsupported assumptions. By doing so, they maintained the distinction between legitimate anomalies that warrant investigation and illusions created by limited perspective or incomplete data. In the end, the analysis reaffirmed a central principle: extraordinary claims require extraordinary evidence. Atlas, despite its remarkable chemistry and behaviour, presented no such evidence. Every observation, no matter how unfamiliar, aligned with known physical mechanisms once the context of interstellar provenance was incorporated. Rather than challenging existing frameworks, Atlas expanded them, offering a more complex but still natural picture of small body diversity across the galaxy. By late November, the speculative noise surrounding Atlas had largely settled. The object's scientific significance no longer rested on the question of what it might be artificially, but rather on what it revealed about the early Milky Way, the diversity of planetary formation environments, and the physical processes governing interstellar debris. The final phase of the investigation, the anticipated December re-emergence, promised to provide the definitive data needed to resolve remaining uncertainties. Whether its structure remained intact or altered, Atlas would soon offer a clearer picture of how its materials responded to the intense heating near the Sun. All that remained was to wait, monitor, and prepare for the moment when the object would once again appear in the pre-dawn sky ready to reveal the next chapter of its interstellar story. As anticipation built for the December re-emergence of 3I Atlas, researchers turned increasingly toward a deeper analytical challenge, reconstructing the object's origin and long-term journey through the galaxy. If Atlas was indeed a messenger from beyond the solar system, then its chemistry, motion, and physical evolution contained information about environments that no spacecraft could ever reach. Interstellar objects act as physical archives, recording the conditions of their birth, the forces that shaped them, and the cosmic history they have endured. Unpacking that record required integrating insights from galactic dynamics, planetary formation, theory, isotope chemistry, and thermal modelling across billions of years. The first clues regarding the object's birthplace emerged from kinematic analysis. By tracing Atlas's motion backward through space, astronomers attempted to identify its parent stellar association. Yet this reconstruction proved far more complex than predicting its forward trajectory. Interstellar objects do not move through a static medium. They navigate a galaxy in constant motion. Stars orbit the Milky Way at different velocities, influenced by gravitational perturbations from giant molecular clouds, transient spiral arms, and tidal interactions with the galactic halo. These forces accumulate over billions of years, erasing linear trajectories and dispersing small bodies across vast volumes of space. Despite these challenges, preliminary modelling suggested that Atlas did not originate in the thin disk, the region where the Sun resides, but rather in the older, more metal, pore-thick disk. This conclusion came from its inbound velocity relative to the Sun, which exceeded the characteristic dispersion of thin disk stars. Thick disk stars formed earlier in galactic history and exhibit distinct chemical signatures, particularly lower ion abundance and altered alpha element ratios. Atlas's unusual nickel to iron imbalance and extreme CO2 levels were consistent with a parent environment shaped by early supernova ejecta and lower overall metallicity. If this interpretation held, Atlas would be older than the solar system itself. Its formation may have occurred during a period when the Milky Way was far more chaotic, when star formation rates were higher and supernova explosions injected heavy elements into the interstellar medium at a rapid pace. Such an environment could produce planetesimals with volatile and elemental compositions significantly different from those observed among solar system comets. Once ejected from its parent system, Atlas would have embarked on a journey through the interstellar medium lasting billions of years. Ejection likely occurred through gravitational interactions with forming giant planets or close encounters with sibling bodies. Simulations of early planetary systems indicate that a substantial fraction of material is expelled during the first few million years of evolution, when planetary migration disk dissipation and dynamical instabilities disrupt smaller bodies. In this respect, the solar system is not unique. Formation simulations suggest that every protoplanetary disk ejects enormous quantities of debris into interstellar space. Atlas, once set adrift, would have traversed regions of interstellar space with densities far lower than any vacuum achievable on Earth, roughly 1 atom per cubic centimetre. In such an environment, surface ices remain stable for geological timescales, though gradual chemical alteration through cosmic ray bombardment is inevitable. High-energy particles break molecular bonds, driving radiolysis reactions that generate new species and alter isotopic ratios. Over millions or billions of years, these modifications can accumulate into measurable changes in surface composition. This mechanism provided a plausible explanation for the depleted water signatures and enhanced CO2 relative to H2O, especially if water molecules were preferentially destroyed or transformed. Interstellar travel also exposes objects to dust grain impacts at high velocity. Even tiny grains can deliver significant energy at relative speeds of tens of kilometers per second, potentially shifting rotational states, darkening surface materials and generating microfractures. These processes could explain Atlas's irregular rotation and the heterogeneous patches inferred from dust jet symmetry. If the nucleus accumulated surface compaction through repeated micro-impacts, it may have developed a strong outer crust delaying sublimation until deeper heating occurred near perihelion. Tracing the object's path also revealed that Atlas likely passed within 1 or 2 light-years of several stars during the past few million years. Stellar encounters of this type are not uncommon for objects wandering through the galactic disk. Each encounter introduces subtle gravitational perturbations that alter trajectory. Although these changes are too small to affect present-day hazard calculations, their cumulative impact over billions of years makes precise origin identification impossible. Instead, researchers rely on statistical reconstruction, determining the most likely stellar population based on velocity and chemistry, rather than identifying a specific star. The thick disk hypothesis offered a coherent narrative, yet it also highlighted the diversity of environments contributing material to interstellar space. If Atlas originated from a region with colder protoplanetary disks, more extreme volatile gradients, or different stellar radiation profiles, its chemistry could preserve features of a planetary formation process distinct from the Sun's. The detection of strong CO2, unusual metal ratios, and layered volatile activation all pointed toward a system where temperature, elemental distribution, and disk evolution diverged from solar system norms. The object's biography also raised deeper questions about galactic ecology. For decades, models of galactic material exchange focused on gas phase processes such as winds from massive stars or supernova-driven mixing. The discovery of interstellar planetesimals introduced a new dimension: solid-state transport of planetary building blocks across stellar neighbourhoods. If objects like Atlas are common, then planetary systems are not chemically isolated. Instead, they may contribute solid materials to one another on timescales, long enough to influence galactic chemical evolution. This perspective prompted researchers to examine whether interstellar delivery could play a role in distributing volatiles or organic molecules across the Milky Way. While Atlas did not carry complex organics in detectable quantities, during its early observation window deeper Laius exposed post-perihelion could contain such compounds. Numerous solar system comets contain amino acids, carbon chains, and prebiotic precursors. If similar materials formed in other planetary systems, interstellar objects could serve as carriers redistributing chemical ingredients foundational to life. Such transfer would be inefficient on short timescales, but meaningful on galactic ones. The idea that Atlas may have spent billions of years as a silent traveller carrying chemical signatures of ancient stellar epochs through the Milky Way fits squarely within this emerging framework. Rather than being an anomaly, Atlas could represent the normone of perhaps trillions of planetesimals travelling between star systems. The solar system itself likely ejects comparable material into interstellar space, joining the same cosmic circulation. By late November, scientific discourse converged on a central implication. Atlas was less a curiosity and more a key data point in understanding how the galaxy recycles planetary materials. Its chemistry dynamics and post-perihelion evolution would help determine whether interstellar objects are chemically diverse, or whether they follow recognizable patterns tied to stellar populations. The December re-emergence would provide the decisive data needed to test these ideas, revealing whether deeper layers preserve pristine materials from a long-extinct protoplanetary disk. What awaited astronomers in December was not merely the continuation of an observation campaign, it was the potential to glimpse through a single object processes that have shaped the Milky Way since long before the Sun existed. As the interstellar narrative surrounding 3I Atlas deepened, scientists began expanding their focus beyond the object itself to consider a broader set of cascade scenarios. These scenarios sought to understand whether Atlas could be part of a larger chain of events affecting the inner solar system. Although most ideas were speculative, examining them served a practical purpose. It forced researchers to test foundational assumptions about small body dynamics, solar influences, and observational biases. Separating physically plausible interactions from fictional ones became essential not only for scientific clarity, but also for managing public expectations during a period of unusually active skywatching. The first category of speculation involved gravitational influence. Popular narratives suggested that Atlas might be stirring up asteroids or triggering the September surge, but gravitational calculations dismissed this quickly. Even at the upper limit of size, estimates Atlas would have a mass far smaller than any planetary body. The gravitational force it could exert on nearby objects decreases with the square of distance, and becomes effectively negligible at astronomical unit scales. For Atlas to perturb asteroid orbits noticeably, it would need to pass within a few tens of thousands of kilometers of the conditions not remotely met during its traversal of the inner solar system. Furthermore, none of the September objects shared the hyperbolic trajectory characteristic of bodies influenced by interstellar gravitational interactions. Their orbits belong to ordinary near-Earth populations well explained by known resonances and long-term evolutionary dynamics. Another popular idea suggested that the object could influence solar activity, perhaps triggering flares or altering magnetic conditions in a way that affected comet behaviour. But solar physics operates on energy scales that dwarf anything a small comet could influence. The Sun outputs more energy in a single second than all human civilization has produced in its entire history. Its magnetic cycles arise from internal dynamo processes unrelated to external perturbations from minor bodies. While it is true that solar wind fluctuations can influence cometary comae or produce complex ion tail structures, the causal direction goes from Sun to comet, not the reverse. A third line of speculation involved meteor showers or interstellar debris streams. The idea was that Atlas might leave behind dust that Earth could eventually pass through, generating unusually bright meteor activity. While meteor showers often originate from cometary debris trails left along stable orbits, interstellar debris behaves differently. material shed by Atlas would inherit its hyperbolic velocity and rapidly disperse through the solar system, never settling into an orbit that intersects Earth's path repeatedly. Such particles would escape the solar system entirely, leaving no persistent trail behind. Even if Earth crossed the object's path months later, the density of dust would be so thin as to produce virtually no visible meteors. Furthermore, any incoming particles would arrive at extreme velocities, producing brief intense flashes rather than the characteristic falling star streaks associated with typical meteor showers. These events would be exceedingly rare. One of the more imaginative scenarios proposed that Atlas might have fragmented long ago, releasing smaller bodies that subsequently entered the solar system as near-Earth asteroids. This idea initially gained traction because of the timing overlap between Atlas's approach and the September asteroid surge. However, fragment trajectories do not align with this concept. Interstellar fragments would retain hyperbolic orbits similar to their parent body. Yet the September asteroids were all gravitationally bound to the Sun and exhibited orbital characteristics consistent with solar system origins. Their spectral properties likewise matched known asteroid taxonomic classes, rather than showing chemical signatures consistent with Atlas. Fragmentation could not explain the clustering. More subtle were concerns about observational bias. Scientists recognized that the September surge might have appeared dramatic only because the observational environment had changed. The Rubin Observatory was beginning to operate at unprecedented cadence. New detection algorithms, more sensitive instruments, and expanded survey coverage meant that objects previously undetected were now being catalogued in rapid succession. Under these circumstances, ordinary variations in asteroid approach timings could easily appear extraordinary. The impression of clustering may simply reflect uneven historical sampling. As detection sensitivity increases, the sky naturally begins to look more crowded. Some researchers explored whether the September events might be part of a longer-term cycle, perhaps related to Earth's passage through denser regions of the inner solar system, where debris accumulates over time. While theoretical models allow for periodic interactions with gravitational resonances, no robust evidence supports a direct link between Earth's current orbital position and a heightened flux of small bodies. If such a pattern exists, it is likely subtle and requires years of continuous monitoring to quantify reliably. A different kind of cascade scenario involved technological and institutional implications rather than physical ones. The simultaneous arrival of multiple near-Earth objects and an interstellar comet stressed global detection systems and raised questions about operational capacity. Analysts pointed out that while the September events were scientifically manageable, a more severe clustering, whether coincidental or not, could overwhelm tracking resources. Planetary defense relies on precise orbit determination, rapid follow-up observations, and global data sharing. A scenario involving multiple potentially hazardous objects arriving within a short window would challenge the system's ability to allocate telescope time and assess risk quickly. This concern was not hypothetical, but grounded in the realities of telescope scheduling, data processing limits, and human decision-making frameworks. Considering such possibilities became increasingly important, as projections suggested that future detection rates could rise dramatically. If dozens of interstellar objects enter the solar system annually, and if near-Earth object discovery rates increase due to improved observational hardware, then brief periods of apparent clustering may become common. In that context, the September experiences provided valuable operational rehearsal. The most intellectually compelling cascade scenario involved interstellar sampling frequency. If objects like Atlas are more common than once believed, the implications extend far beyond planetary defense. Each interstellar visitor carries information about exoplanetary chemistry, early stellar environments, and galactic mixing processes. A regular influx of such material would transform the study of planetary formation across the Milky Way, enabling direct sampling of volatile inventories and primordial dust populations from numerous stellar systems. The conceptual shift triggered by this possibility was significant. Rather than interpreting Atlas as an isolated anomaly, researchers began contemplating its role in a larger galactic system of material exchange. In this perspective, Atlas was not an outlier, but one data point in an enormous statistical ensemble. Its properties reflected not personal uniqueness, but the diversity of conditions under which planets and small bodies form throughout the galaxy. Studying Atlas therefore meant studying the Milky Way itself on a small concentrated scale. By late November, these inquiries had established a clear conceptual boundary, while cascade ideas involving gravitational perturbation, solar effects or meteor storms lacked physical grounding scenarios related to detection capabilities. Interstellar population estimates and scientific opportunity were well supported. The true significance of Atlas did not lie in influencing the solar system, but in what its existence revealed about galactic dynamics and the solar system's porous relationship with its surroundings. As the expected December re-emergence approached, the conversation shifted once again from possibility to empirical anticipation. Whatever the speculative debates had suggested, the next round of observations would provide direct answers regarding Atlas's structural survival, chemical evolution, and rotational state. The object was about to reappear, and with it the clearest window yet into the material legacy of another star. As the calendar turned toward the final days of November, astronomers prepared for one of the most technically challenging yet scientifically invaluable periods of the entire Atlas encounter, the post-perihelion observing window. Atlas had now passed within 44 AU of the Sun closer. The Mercury end was entirely obscured by solar glare. For weeks, the object had been inaccessible to ground-based telescopes, leaving researchers uncertain about its structural integrity and chemical evolution. The transition into December promised not only renewed visibility, but the most scientifically revealing phase of the object's journey. The geometry of Atlas's reappearance was favourable in principle, but demanding in practice. As Earth continued along its orbit, the comet gradually separated from the Sun's glare, emerging into the pre-dawn sky. This slow drift allowed increasingly sensitive observations, beginning with wide-field images and progressing toward high-resolution spectrographs. The critical challenge was maximising the narrow observing windows available before dawn, while contending with atmospheric interference, low elevation angles, and rapid changes in brightness as the comet warmed, cooled, and expanded its coma. This phase carried heightened interest because perihelion is when comets typically undergo the most significant transformations. Solar radiation penetrates deeper into the nucleus, triggering activation of volatile layers that remained dormant during earlier phases. In many cases, comets fragment at this stage as internal pressure, thermal stress, or structural weaknesses exceed their mechanical limits. The key unknown was whether Atlas had survived as a coherent body. The answer would have profound implications for models of interstellar object resilience. If Atlas remained intact, it would suggest a nucleus structure more cohesive than that of most Oort cloud comet, potentially reflecting either a unique formation environment or extensive compaction during its interstellar voyage. If it fragmented, the resulting debris distribution could provide insight into internal layering, volatile reservoirs, and tensile properties shaped over billions of years. Either outcome would offer rare evidence about the structural evolution of small bodies exposed to interstellar conditions. The observational strategy for December involved a coordinated global campaign. Southern Hemisphere observatories with more favourable early morning geometry at first reappearance were tasked with initial recovery attempts. Instruments capable of capturing faint diffuse structures were prioritised. Sensitive CCD images, low-resolution spectrographs, and wide-field telescopes designed to detect extended coma features. Once the comet brightened, sufficiently large facilities such as the Very Large Telescope and Gemini South could begin detailed characterization. Researchers expected 3 possible observational signatures during re-emergence. The first and simplest was the return of a single coherent nucleus with a stable coma. This scenario required Atlas to survive perihelion intact without undergoing major structural modification. The second scenario involved partial fragmentation. In this case, multiple discrete brightenings or separated dust concentrations might appear in images forming a fan-like pattern or a chain of fragments. The third possibility, a total disintegration, would produce an expanding cloud of dust with no visible central condensation rapidly dispersing under solar radiation pressure. Fragmentation probabilities depended heavily on Atlas's internal composition. If the nucleus were dominated by CO2, rich ice's sublimation near perihelion could have generated high internal pressures. On the other hand, if interstellar processing had produced a reinforced crust, it might have dampened thermal gradients and prevented catastrophic failure. Researchers also considered the possibility of asymmetric erosion solar heating on one hemisphere could cause uneven mass loss, potentially altering rotational state or triggering structural torque. Another key goal of the post-perihelion window was to measure non-gravitational acceleration. Sublimation-driven forces often change after perihelion as new volatiles become exposed. These forces, detectable through slight deviations in the comet's trajectory, provide information about localized outgassing patterns and internal structure. For Atlas, post-perihelion acceleration could help identify whether deeper layers contained volatile species distinct from the surface materials seen pre-perihelion. Equally significant was the spectroscopic component. With the object now warming from the opposite direction, different chemical pathways could become active. Researchers hoped to detect water signatures that were weak during the inbound phase or unusual molecules that had not yet sublimated. The high CO2 content hinted at a volatile inventory, not dominated by water, but deeper layers could tell a different story. Infrared spectrographs on JBUST and ground-based facilities were prepared to monitor rotational transitions, broadband features, and potential isotopic ratios. Changes in coma morphology would also provide important clues. Prior to perihelion, Atlas displayed jets with diverse orientations and dust-size distributions. If the nucleus had been structurally modified, these jets might shift or disappear entirely. New sources could emerge from regions previously shadowed from solar radiation. Observing such transitions in real time would offer a dynamic map of the nucleus's internal heterogeneity. One of the most conceptually significant aspects of the observing campaign involved comparing Atlas's thermal evolution to that of solar system comets. Comets entering the inner solar system for the first time often behave erratically, lacking a hardened mantle formed by repeated passes. Atlas, however, had no history of solar heating. Whatever crust it possessed was shaped by interstellar exposure, not solar radiation cycles. This meant its response to perihelion offered a window into how raw interstellar materials respond to stellar environments. If the object's surface experienced rapid thermal fracturing, producing new jets, dust plumes, or fragmentation, would support models predicting that interstellar ices are structurally delicate upon contact with intense stellar heat. Conversely, if Atlas maintained structural cohesion, it would imply that cosmic ray processing and micro-impact compaction can produce outer layers strong enough to withstand rapid temperature changes around Sun-like stars. Beyond the physical and chemical implications, the re-emergence offered a rare opportunity to refine galactic models of material exchange. By analysing how Atlas's deeper volatiles behaved, scientists could estimate the temperature ranges and pressure conditions of its formation environment. This in turn would inform models of protoplanetary disks in the thick disk or other ancient galactic regions. Each volatile signature served as a chemical timestamp preserving the state of the galaxy billions of years ago. The December observing window also carried logistical importance. Coordinated monitoring would test International Observation Network's ability to track rapidly evolving phenomena. Lessons learned from Atlas's re-emergence would apply directly to future interstellar objects, and more urgently to hazardous comets approaching from solar-blind regions. As November drew to a close, the global astronomical community entered an unusual period of collective suspense. The object that had travelled billions of years through interstellar space was about to reveal whether it had survived its close encounter with the Sun. For the moment, only one uncertainty remained: would Atlas return as a coherent body, a scattered filament of dust, or something in between? Whatever the answer, its reappearance would provide empirical data that no simulation could fully replace. It would offer a final opportunity to observe an object shaped by a place and time far beyond the solar system, an ancient remnant of galactic evolution, emerging from the Sun's shadow into the brief window of human scientific attention. As December arrived and 3E Atlas began its slow emergence from behind the Sun, the initial observational returns provided the first concrete insights into the object's condition after perihelion. Wide-field images in Chile and South Africa were among the first to detect a faint diffuse glow at the predicted coordinates. The earliest images were inconclusive, an elongated patch of light that could have indicated survival fragmentation or simply a low-signal coma unresolved by small telescopes. Over the following days, however, as Atlas rose higher in the pre-dawn sky, the structure sharpened enough to allow preliminary interpretation. The first major finding was that Atlas had not undergone total disintegration. A central condensation remained visible, indicating that at least one substantial fragment of the nucleus persisted. This alone had significant scientific implications. If the object had survived perihelion largely intact, it suggested a mechanical strength, exceeding that of many solar system comets, which frequently undergo catastrophic breakup when exposed to similar heating. Atlas's endurance supported hypotheses that interstellar processing, cosmic ray compaction, micro-impact sintering and surface densification could strengthen small body surfaces over long timescales. Yet survival did not imply stability. Early photometric measurements revealed fluctuations more extreme than those observed pre-perihelion. The brightness varied from night to night, suggesting active reshaping of the coma and possibly ongoing fragmentation processes. A faint secondary condensation, tentatively interpreted as a daughter fragment, appeared in some exposures, but not others, implying either transient dust structures or a fragment too small for consistent detection. If confirmed, such fragmentation would align with models predicting that deeper layers of the nucleus, now exposed to solar heat for the first time, contained volatile reservoirs capable of inducing structural stress. Spectroscopic analysis began once brightness stabilized enough for slit-based instruments to capture meaningful data. Preliminary results showed a notable shift in volatile composition. The strong carbon dioxide dominance seen during the inbound phase persisted, but water vapor emissions increased significantly. The rise in H2O suggested that perihelion heating had penetrated deeper layers, reaching reservoirs that were previously insulated by the surface crust. This transition supported the idea that Atlas possessed a stratified internal structure, with outer layers dominated by CO2-rich ices and deeper layers containing more familiar volatiles. The detection of water vapor also enabled measurement of the DH ratio key isotopic fingerprint, often used to trace the history of volatile reservoirs. Solar system comets exhibit a wide range of DH ratios, reflecting diverse formation environments within the protosolar nebula. If Atlas exhibited a DH ratio markedly different from solar system objects, it would provide direct insight into the conditions under which its parent system formed. Early values hinted at enrichment relative to terrestrial water consistent with extremely cold formation temperatures, but uncertainties remained too large for definitive conclusions until higher. The December window also reinforced the connection between interstellar object research and planetary science. The resilience of Atlas suggested that interstellar planetesimals might survive encounters with young planetary systems, potentially contributing volatiles or prebiotic compounds. If such objects regularly traverse the Milky Way and occasionally intersect forming solar systems, they could play a small but meaningful role in distributing chemical ingredients necessary for habitability. By late December, Atlas began to fade as solar heating decreased, and the object receded toward the outer solar system. While observational conditions deteriorated, the scientific impact of the encounter continued to grow. The months-long campaign produced a uniquely complete data set, covering inbound behavior, perihelion response, and post-perihelion evolution. Together, these observations revealed an object shaped by an environment far older and more diverse than the Sun's carrying material imprints of a long-extinct protoplanetary disk and the deep interstellar medium. Atlas's departure marked not an end, but a beginning. The data it provided would inform models of planetary formation, interstellar chemistry, galactic evolution, and small body dynamics for many years. Its brief passage through the inner solar system demonstrated that even a transient visitor can expand the scientific horizon, offering a direct glimpse of the Milky Way's distant past through a single icy remnant drifting back into the dark. As our exploration comes to a gentle close, traveller, the sky feels different than it did when we began. We traced the motions of asteroids, the brightening of distant comets, and the quiet persistence of 3i Atlas as it approached Mars. Yet what lingers now is not a single discovery, but the sense that we have brushed against a much larger truth. The universe is not still. It is not silent. Even in its quietest hours, new objects continue to drift into view, each one carrying a fragment of history from places we may never reach. The patterns we observed are not accidents. They are reminders that our solar system is part of a wider circulation of matter, a vast exchange shaped by gravity time and the slow breathing of the galaxy itself. In witnessing these events, we learn something about ourselves as well. We are small, yes, but our curiosity gives us a place in this immense story. To look upward is to participate, to wonder is to belong, and to accept the unknown without fear, without rushing toward answers, is its own form of wisdom. As you settle into rest, let that understanding stay with you. Some mysteries do not demand solutions. They invite quiet attention. The night is long, traveller. Sleep well. The universe will keep watch.